Welcome to this visual explainer. Okay, picture this. You're straining, muscles are absolutely burning, trying to lift this ridiculously heavy box with your bare hands, and it's barely budging. Yeah, we've all been there. It's an incredibly frustrating, sweaty struggle. But what if you took that exact same box, hooked it up to a simple rope and a wheel, and suddenly you lift it like it's nothing? It's almost like gravity just packed up and took a vacation. That incredible transformation is exactly what we're going to be exploring today. It really makes you wonder, right? Like, seriously, how does one single person possibly lift an entire super heavy car engine? Or, let's think even bigger, how do those giant, towering construction cranes effortlessly hoist literal tons of steel and building materials all the way up to the peaks of skyscrapers? It looks like absolute magic, but the answer actually relies on one of humanity's oldest, most brilliant, and honestly, simplest machines. Here's our roadmap for today. We'll uncover the superpower secret, define what is a pulley, compare fixed versus movable pulleys, look at complex systems and Newton's law, and finally, wrap up with everyday pulley applications. Section 1. The superpower secret. Let's look at those hidden lifting forces. Okay, let's dive into this. In the world of dynamics and physics, a pulley is brilliantly straightforward. At its core, it's really just a wheel on an axle or a shaft designed to support movement. Around this wheel, there's a groove, and through that groove runs a rope, a cable, or a belt. It's such an elegant, ancient design, but it entirely changes how we interact with heavy loads. So what does it actually do? Well, the absolute core functions of a pulley are either to change the direction of your force or to significantly reduce the physical effort you need to lift a weight. Think about it. When you grab that rope and pull downward with your body weight, the pulley transforms that downward physical force into an upward tension that effortlessly lifts the mass. You pull down, the weight goes up. Now, to really understand the math behind all this, physicists use something called the ideal pulley scenario. Whenever we're analyzing these systems, we start by assuming the pulley wheel is completely frictionless. We also assume the rope is massless and inextensible, which basically just means it doesn't stretch like a rubber band. Now, obviously, perfect conditions don't quite exist in reality, but this theoretical baseline is absolutely essential. It allows us to simplify the mathematical calculations and cleanly map out the core dynamic forces that are at play. Section 3. Fixed versus movable pulleys. Let's break down the two functional types. First up, we have the fixed pulley. Just as the name implies, the wheel of this pulley is firmly and permanently attached to a stationary structure, like a solid ceiling or a rigid wall. When you pull the rope, the wheel spins, but it doesn't actually travel up or down with the load. It stays exactly right where it is. So the crucial point is that a fixed pulley doesn't actually reduce the total force you need to exert. If you have a weight that exerts 100 newtons of downward force, well, you still have to pull with exactly 100 newtons of force to lift it. So you might be wondering, why even use it? Because it makes lifting infinitely more comfortable. Instead of straining your back trying to heave something straight up, a fixed pulley lets you pull downward, which allows you to use gravity and your own body weight totally to your advantage. Secondly, we have the movable pulley. And honestly, this is where things get genuinely exciting. Unlike the fixed version, a movable pulley isn't attached to a ceiling. Instead, the wheel is attached directly to the load itself, and it travels up and down simultaneously with whatever you're lifting. This setup builds to a massive physics surprise. Now, what's really interesting about this slide is the sheer magic of the math here. With a movable pulley, the required force is literally cut in half because the rope is anchored on one side, looping through the pulley, and being pulled by you on the other side. The rope is actually supporting the weight from both sides. Therefore, to lift that exact same 100 Newton weight, you only need to apply 50 newtons of pulling force. You are lifting the same weight with half the power. How amazing is that? And this brilliantly illustrates the ultimate cosmic trade-off in physics. You know, you never get something for nothing. With the fixed pulley, your 100 Newton load requires 100 newtons of pull, and you pull the rope in equal distance to how high the object rises. But with the movable pulley, while you enjoy the massive benefit of only needing 50 newtons of force, there is a tax. To lift the object 1 meter, you have to pull 2 meters of rope. That's the golden rule of mechanics. Using half the force requires pulling the rope twice the distance. Let's move to and see how this builds into Section 4, Complex Systems and Newton's Law. When mechanical engineers need to lift something truly monumental, they don't just use one pulley. They create a block and tackle system. This is an ingenious integration of multiple fixed and movable pulleys all working together in tandem. As you weave the rope through more and more movable pulleys in this complex system, the physical effort required to lift the load decreases astonishingly. It's literally how human beings multiply their strength exponentially. But to build these safely, engineers can't just guess. They strictly rely on kinematic dynamics. Specifically, they rely on Sir Isaac Newton's second law of motion: force equals mass times acceleration. This foundational equation is the lens through which we study and design these complex, heavy lifting systems to ensure they work perfectly every single time. Analyzing these forces involves a few very clear, approachable mathematical steps. First, we identify the downward force of gravity acting on every single mass in the system. Second, we identify the upward tension force running through the ropes. Finally, by writing out the equations of motion for all the connected masses, we can accurately calculate the overall acceleration of the system. More importantly, this math determines the maximum tension the cables can handle before the loads cause them to snap. It is precision engineering keeping everything safe. All right, Section 5, Everyday Pulley Applications. You might not realize it, but you interact with the magic of pulleys constantly. Just think about the elevators seamlessly moving you between floors in a high-rise. Think about the cable machines you use at the gym to train your muscles. Picture sailboats harnessing the wind, or those massive construction cranes we mentioned earlier, lifting city skylines into existence. Pulley dynamics are not just abstract concepts for a textbook. They form the absolute backbone of modern mechanical engineering and architecture. All of this beautifully embodies the profound philosophy of mechanical advantage. The ancient Greek mathematician Archimedes once famously said, "Give me a place to stand and I shall move the earth." And he was totally right. He understood perfectly well that with the right mechanical leverage, like a cleverly designed system of pulleys, human capability is virtually limitless. So, I leave you with this question. If you could design a pulley system to effortlessly lift any heavy weight or burden in your own life, what would it be? Think about the incredible mechanical superpower you now understand. If you enjoyed today's visual explainer, don't forget to hit the like button and subscribe to the channel to discover more secrets of physics and dynamics. Thank you so much for joining me, and I'll see you in the next explainer.